So let's go. I'm going to talk about, we talked about last week and in the videos, uh, substitution by SN2, the one-step reaction. And we talked about elimination by E2, which is also a one-step reaction. But there's two other mechanisms of substitution and elimination that go by more than one step, and those are SN1 and SN2. And I want to talk about those now. Oops, I want to move this over, sorry. Okay, I want to talk about those now. So here's a substrate right here. Here's a reaction of a tertiary, this is a tertiary substrate. And we dissolve it in a solvent. So we don't have an anion, we don't have a hydroxide or a methoxide or a cyanide or any anion that can act as a nucleophile. The solvent is the nucleophile. It's ethanol. And you see that you get a mixture of products. You get a substitution product where the ethanol replaced the bromine. Notice the oxygen of the ethanol is lost in H+. We also get a product of an elimination, an alkene, that results from removing this beta hydrogen and kicking out the leaving group. So it turns out that in these reactions, the kinetics are not second order. The kinetics are first order. And so that tells us the SN2 and E2 reaction is not taking place, because remember, both the SN2 and E2 reactions follow second order kinetics, which are first order in the substrate and first order in the base or nucleophile, because both are involved in the reaction, in the rate limiting reaction. But this reaction up here, it follows first order kinetics. It only depends on the substrate concentration. And so you can see why SN2 and E2 don't occur. First of all, the substrate's tertiary, and so it's too sterically crowded, so SN2 doesn't happen. And the reagent is as an alcohol. The reagent is an alcohol, which is a very weak base. And so E2 is also not favored. Remember, E2 depends on the concentration of base, and it's sensitive to the strength of the base. And so when you have a weak base, that slows down that reaction dramatically. So neither of those reactions are favored, SN2 or E2, and that's reflected in the rate law. That's only first order. So what's going on? Okay, let's take a look. Okay. So what's going on is that there's a different mechanism. It's a stepwise mechanism where the first step is loss of the leaving group. Okay. You see the leaving group breaks off. You form the carbocation intermediate. Okay. Form the carbocation intermediate. And then that intermediate can either react with a nucleophile to form a substitution reaction. That's called SN1. Substitution, or it can react where the nucleophile acts as a base, attacks the beta hydrogen and forms an alkene, the elimination product, that's E1. Okay? So in this reaction, if you ionize to form a carbocation, and that can partition to form either substitution or elimination products. You typically get mixtures in these cases. So what I'd like to do is look at the two pathways, SN1 and E1, and I'm going to look at the SN1 pathway first, okay? Okay, so let's clear this. So the SN1 pathway, this is the details of it. The first step is loss of the leaving group. The CBr bond breaks. You get the carbocation intermediate, okay? And now in this case, the solvent is ethanol, but you'll see you can have various solvents. You can have water, you can have methanol. The ethanol acts as a nucleophile. The oxygen attacks the positive carbon. So you're getting nucleophilic attack here. That's up here. and you form this product. Because this still has an acidic hydrogen, you get a step where it loses its proton. A second molecule of ethanol takes off the proton, and you form the such substitution product, which in this case is an ether. So the actual mechanism is 3 steps: loss of a leaving group, nucleophilic attack, and then you have this proton transfer to neutralize the product, okay? But the key steps are the loss of the leaving group and the nucleophilic attack. Now, when the nucleophile is the solvent, which it is here, not an anion, the reaction is called a solvolysis. The reaction is called a solvolysis. Okay? When the reaction is when the nucleophile is the solvent. Okay? So here's an energy diagram of that. And so we're starting here with the reactant, right? And the first step is loss of the leaving group. It gives you the carbocation, right? Then you have the nucleophilic attack. In this case, the nucleophile is the solvent ethanol. So you get nucleophilic attack over this barrier to give you the acidic or protonated product. And then you get a final proton transfer to give you the final substitution product, okay? So you see the highest energy transition state is this one. That's the highest energy transition state. And the highest energy transition state is called the rate determining step. That's the step that affects the overall rate of the reaction, okay? So you see this step, the slow step, the rate determining step, only involves the substrate concentration. And because that first step only involves the substrate concentration, the rate reflects that. The rate is proportional only to the substrate concentration, and that's reflected in first order kinetics. The base, the ethanol base or nucleophile does not come into after the rate determining step. So the rate determining step only involves the substrate ionizing, and so the rate reflects only the substrate concentration in the rate law. And so this is where the SN1 symbolism comes from. S stands for substitution reaction. N stands for the fact it's promoted by a nucleophile. And 1 is unimolecular. It's a first order rate law, okay? Okay, there we go. So I want to show you, this is an important slide that summarizes a bunch of things. So there's the energy diagram for the reaction where I showed you before. Here's the rate determining transition state. So the rate determining step, what does it involve again? Let's summarize it. It involves loss of the leaving group and formation of the carbocation. And that's shown here. So this is the rate determining step. That's step 1 of the reaction right here. And this is the step here. That's the step here, right? And this is the transition state for that step. And notice the transition state. That's the structure at the top of the hill. And notice the bond to the leaving group is breaking and the positive charge is developing, right? Right at that point. And that continues and the bond fully breaks. You end up with bromide ion and the full carbocation, right? Now, so the rate of these reactions, the SN1 and the E1-2, this is what increases their rates, okay? So we saw steric effects strongly affect an SN2 reaction. And the SN1 and the E1 is the same, because it has the same rate determining step. The rate increases with better leaving groups. Why? Because the bond to the leaving group is breaking. So the better the leaving group, the easier it is to break that bond. And the order of leaving group ability is iodide is better than bromide, is better than chloride, which is a heck of a lot better than fluoride. Okay, that reflects base strength. Iodide is the weakest base, Then bromide's next, chloride's next, and then fluoride is the strongest of these bases, so it's the poorest leaving group. The other thing that increases reaction rate is forming more stable carbocations, right? So if you see you're forming a positive charge here, so the better this positive charge is stabilized by the substituents, the faster, the more stable the transition state will be, the lower its energy will be, and the faster the rate. So more stable carbocations speed up the reaction. So what order would we expect? Tertiary now is the most stable carbocation, then secondary, then primary, then methyl, right? You notice that? Most stable carbocations, tertiary, they react fastest. Least stable carbocations, methyl, react slowest. That's opposite the order in an SN2 reaction. Totally opposite, okay? And then finally, the reaction is favored by polar protic solvents. So remember, SN2 is favored by polar aprotic solvents, which make the nucleophile, the anionic nucleophile, more reactive. Here it's polar protic solvents, like protic means it can donate a hydrogen bond. Protic means it can donate a hydrogen bond. And so the most common ones would be water, methanol, and ethanol, okay? Why is that? Why is that? Well, the polar solvent stabilizes charges. The more polar a solvent is, the more better at stabilizing charges. So you see the transition state charges are developing. And furthermore, these species which can hydrogen bond to the Br minus that's forming. And stabilize it. So the polarity favors the charge separation, and the hydrogen bonding ability of these protic solvents stabilize the leaving group. Both of those lower the energy of the transition state and raise the reaction rate, okay? So better leaving groups, more stable carbocations, and polar protic solvents facilitate SN1. And we'll see E1 reactions too, because they have the same rate limiting step, okay? So now I'm going to test your understanding or your memory, perhaps. Well, before I do that, let me just show you here the difference of solvents. These are all polar protic here: water, methanol, ethanol, and these two are polar aprotic. Well, acetone's polar aprotic. Diethyl ether is just aprotic. And you see the measure of polarity is the dielectric constant. The higher it is, the more polar it is. So water is the most polar, then methanol, you see, and ethanol, and acetone. You see, diethyl ether is very low polarity. Can't dissolve a salt in diethyl ether. Try to dissolve sodium chlorine diethyl ether, it just sits on the bottom. It's not polar enough, okay? And look at the rates of SN1 reactions, this particular reaction. See, the more polar one is setting the rate at 1 for the ethanol reaction, 40 times faster in the more polar water. Look how much slower it is in these solvents that are less polar and cannot hydrogen bond, okay? So that's an example of how polar protic solvents facilitate SN1 reactions. SN2s, remember, were facilitated by polar aprotic. Okay, so now I will, this is just a diagram showing you the reaction and how in a nonpolar solvent, the carbocation energy is high, and in a polar protic solvent, the transition state, actually it's the transition state, is stabilized in the way we do, and so the whole activation barrier is lowered and the reaction is much faster. Looks like we have a question. Cameron, can we determine if it's SN1 or SN2 based on the solvents? That's a good question. And the answer is you can't, generally the solvents will favor SN1 and E1, not favor SN2 or E2 because the SN2 and E2 rates are second order. They depend on the substrate concentration. They depend on the base concentration. And so when the base is really weak, when you have a solvent which is the nucleophile, which is very weak, that dramatically slows down the SN2 and E2 reaction. And it favors the SN1 and E1. The polar product nature of those solvents facilitate the ionization. And that's a factor too. Okay, I hope that answers your question. Okay, another question. Okay, yes, it does, it does. And I don't want to get too much ahead of myself, but I'm going to show you a slide later that summarizes all this in a table. Okay, so hang on a little bit more if you can, and I'll show you. But that is true. Generally, solvents or weak bases generally don't even think SN2 in those cases. They're just too slow. The reactions are too slow. Just think SN1. If you're going to get a substitution and you have a solvent as a nucleophile, just think SN1. Okay. Okay, so now I want to move on and test your understanding. It's not a quiz. I just want to see how much you remember about this. So the question is, you can't see it, but which of these is faster in an SN1 E1 reaction? Okay, which is faster, the chlorocyclopentane or the bromocyclopentane? So maybe I'll just let you think and I'll answer it for you. So the only thing, what you do here when you compare reactivities is the only thing you see what's changed, and the only thing that's changed apparently is the leaving group, right? Nothing else has changed. It doesn't, okay, and so remember, bromide is a weaker base than chloride, and so this one will be faster. The better leaving group, iodide is better than bromide, better than chloride. The bond to the leaving group will break faster, all other things being equal, that will react at a faster rate. Okay, okay, let's look at the second one. So here, the leaving group is the same, so that can't explain it. Presumably everything else is the same, otherwise we would be given that information. And so since we're talking SN1 here, we need to look at the carbocation. So I'm gonna break the bond here, and we're gonna draw this carbocation. All right. That would be that carbocation. Okay, question, let's take a look at that. Kylie, you mean the first example? Yeah. The reason the bromide reacts faster is because the SN1 reactions depend on how good of a leaving group you have. Because the bond to the leaving group is breaking. And so the better the base, the weaker the base the leaving group is, or the more stable it is when it leaves, the faster it'll react. And so the rate of leaving, bromide is a weaker base than chloride. It's a better leaving group. You can just remember it as being a better leaving group. And so that bond will break more easily and the reaction will be faster. Okay, I hope that answers your question. Okay, and so let's look at the other carbocation here. Okay, this is good. Okay, thank you. Thanks for asking that. So now let's look at the loss of the leaving group here. We'll lose the leaving group there. And so now we gotta remember we have a double bond here. Okay, so we form that carbocation. So which one is more stable? This is primary. This is a primary carbocation, one carbon attached. This is a primary carbocation, but we can't forget what we've learned before. This is an allylic carbon. It's a carbon attached to a double bond. And so this is an allylic positive charge, and that's one of the resonance patterns. And you can just take this arrow pi bond and move it there. Right? Now the positive charge moves there, right? So this carbocation from this substrate is stabilized by resonance. You can spread out or delocalize the positive charge over these two carbons. And whenever you have resonance or delocalization, that stabilizes the species. So this is a more stable carbocation than this one. And so it forms faster, right? It's more prone to form because it's more stable, okay? The more stable the carbocation, the faster the SN1 reaction, okay? So we talked about tertiary being secondary, better than secondary, being better than primary, but resonance can increase the stability of any of those, okay? Okay, let's look at the next one. Okay, what about this one? Let me clear this. Okay. So let's look at these two. This is going to be similar. I'll look at this one first. We're looking at an SN1, so we have to ionize and look at the carbocation. Right? We're going to break this bond. That's primary. And then in this case, we're going to break that bond. It's a benzene ring. And we get another primary. By the way, if you don't mind me, let me point this out. This carbocation formed here from this substrate. This is called an allylic carbocation. Because the positive charge is on a carbon, allylic is an allylic carbon, all right? So which one's faster? So the answer is this one, and it's for the same reason. You see, this positive charge is also allylic to the benzene ring, to this double bond here. And so you can take the pi bond and move it here. Allylic positive charge. Oops, sorry. That's gone, right? A double bond, all right? And there are several other forms you can draw. This is a little positive charge is allylic to this double bond. I'll draw one more. You can do this. By moving this pi bond here, this carbon loses a bond. It becomes positive. Right? There's several more you can draw, but you see, these are resonance stabilized. This one is not. So this will react faster. And a positive charge on a carbon attached to a benzene ring is called a benzyl carbocation. So both allyl carbocations and benzyl carbocations are stabilized by resonance. So even though this is primary, the resonance increases its stability. It's probably more like a secondary because of the resonance. Okay. All right. I hope that was good. Oh yeah, last one. So what about this one down here? So you look, the only thing that's changed is the solvent that the reaction is run in. So this is a solvent effect. The first one was a leaving group effect. The next two were effect of the stability of the carbocation. And this is a solvent effect. And of course, if you remember, water is the most polar solvent, so that is faster because it facilitates the ionization of the substrate to form the carbocation. So it'll be significantly faster in water than in the less polar ethanol solvent. Okay, okay guys, I hope that's helpful. Yeah, so now I want to continue with SN1, and I want to look at the stereochemistry. So it's important to compare, let's say, compare the stereochemistry of an SN1 with SN2. Now, I emphasized this point in when we went over the quiz, that SN2 involves inversion of configuration, backside attack. If you have a chiral carbon, that has the leaving group, if it's S to begin with, it'll be R. If it's R to begin with, it'll end up in S. But the stereochemistry of SN1s is entirely different, and I'll show you why. So here we're starting out with a substrate that's chiral, right? We have a chiral carbon here. And in SN1, the first step is ionization. So you lose the leaving group, right? You're losing the leaving group. You form a carbocation. Okay, we're forming the carbocation. Why are we drawing it like this? Well, the carbon of this carbocation has a steric number of 3, right? So it's trigonal planar. It uses sp2 hybrid orbitals to form the bonds, the 3 groups. And it has an empty p orbital. See, that's the p orbital, right? And that p orbital is perpendicular to the plane of the molecule. We're drawing it edgewise. Okay. So now when a nucleophile comes in, a solvent, typically for SN1, where is it going to form a bond? Well, you see, it can form a bond. It can come in and form a bond on the right side, right? Or it can come in and form a bond on that side, the back side, right? What's stopping it? Nothing from going. It's flat. It can go either side. So the bromine left from the right side. And so if it comes in from this side, the nucleophile ends up on the same side as where the bromine started. And that gives you something with what we call retention of configuration. Okay. If this substrate was S, this will also be S. Right? And now if it comes in from the opposite side of where the bromine started, then the nucleophile will end up in the back side, and you'll have inversion of configuration, and the product will be R. So what do you get here? Well, what you get is you get a mixture of these. Theoretically, you should get a 50-50 mixture, because the probability of coming in from the right side or left side on this planar carbocation is the same. So you're starting with a chiral molecule that's optically active, and you ending up with a racemic mixture. Okay, if you get 50-50, you'd have a racemic mixture, and that is called racemization. So whereas in SN2 reaction, you don't lose the chirality, you still have a chiral carbon at the end. It just has an opposite configuration. In an SN1, you lose the chirality. You form generally a racemic mixture. That process is called racemization. Okay. So I want to show you that's not 100% true. Oops. So here's an actual reaction. Oh yeah, sorry. So here's another slide that shows you actually what is observed. It's not exactly 50-50. So here's a carbocation, and the bromide has left, right? The bond is broken, but the bromide is still in the vicinity of the positive charge. So the negative bromide is kind of attracted by the positive carbon. So this thing is called an ion pair. Now, it will eventually diffuse away. It will eventually an ion pair. The bromide will diffuse away and it'll be gone, but initially it's nearby. And so the nucleophile attack on this side is a little more hindered by the bromide that's in the vicinity. And so more of it comes from the backside. And so you get slightly more inversion than retention in SN1 reaction. It's not pure racemization. I'll show you an example of actual reactions. Here's an actual reaction where you have the nucleophile is iodide. It's under SN1 conditions. You see you get, this is S, this is an S bromide. You get 55% of the R and 45% of the S. So you get a slight favoring of inversion, okay? It's almost pure racemization, okay? Right? Okay, guys? So that's a big difference between SN1 and SN2. So let's predict the products of this SN1 reaction. So you see, sometimes you don't need with tertiary substrates, which strongly disfavor SN2, with weak enough nucleophiles, even some anions, you can get SN1. But the more common situation is with the solvent. Okay, and, you know it's SN1 when I'm telling you that. And so what's the product? Well, you're going to lose the leaving group. And I'm not going to actually show that. And you get a carbocation, right? Whoops, I don't know why I drew that at an angle, but okay, I don't like that. So let me put the ketone in, and you have the bromine came off the carbocation form, and this is an acetate ion. This is what it looks like if you draw it out. So the acetate can come in from the same side, right? I'm going to draw it out. It came in from the same side, the bromine, and then the methyl would be stay down. And because the carbocation can be attacked from either side, the acetate could also come in from the back side, right? It's a flat carbocation. Then the methyl would be pushed up, okay? So you're going to get roughly a 50-50 mixture of these. You get a slight excess of the inverted product, but you can think of this as roughly a racemic mixture, okay? If this was SN2, you'd get one pure stereoisomer, okay? Okay? So something approaching racemization when you have SN1. Well, let's see what's next. Okay, so that's the SN1 and what you need to know about it. Now, the E1, I want to comment on this. The E1 and SN1 have the same rate limiting step, and they occur when one occurs, the other one occurs. And they're not very good reactions in organic synthesis, because in organic synthesis, you don't want a reaction that gives you mixtures all the time, and you have the problem of having to purify the mixture. But we're going to talk about this so we understand a little more about fundamental chemistry. So when the leaving group leaves, this is the same substrate we were talking about with the SN1. The bromide leaves, you form a carbocation. So the solvent we saw can attack the positive carbon and form a substitution product, right? We saw that in the previous slide. But it can also attack the beta hydrogen, as shown here, right? And then the electrons here go between here to form a double bond. So that's the elimination product, and this is the E1 mechanism. E because you're getting an alkene, an elimination product, not a substitution. 1 because the slow step, the rate determining step, only involves one molecule. Okay. Yeah, here's the energy diagram for this. The leaving group leaves. Here we have a generic leaving group. We get the carbocation. This is the rate, the highest energy transition state. That's the rate determining step. And we can either, the carbocation can react with the nucleophile to form a substitution product, that's SN1, or it can lose a beta hydrogen to form an elimination product, alkene, that's E1. So you see the E1 and SN1 has the same rate limiting step. So it follows the same rate law, and you'll get a mixture of products. In this particular energy diagram, you see the substitution is a little faster. It has a lower activation barrier. You get a little more of that, but you'll get mixtures all the time, okay? Because that carbocation it has a tendency to do both, react with this, the nucleophile and lose a beta hydrogen. Oops, sorry, what's happening here? Okay, there you go. So here's probably the last thing we'll talk about for today's class. And because SN1 and E1 reactions go through the carbocation, you can sometimes get rearrangements. And I'm going to remind you about that. Remember, carbocations can undergo hydride or methyl shifts. So let me show you this, and I'll explain it exactly what's going on. All right. So here's your substrate here. We're starting with this substrate, and now the solvent is water. Excuse me. Solvent is water. So we're talking about SN1 E1 reactions here. You lose the leaving group, you form a carbocation, and then the substitution product involves water replacing the bromide. And notice the water loses H plus. It initially attaches as H2O, and then it loses the acidic hydrogen. So the SN1 product's an alcohol, and you see we're getting two of them. We'll see why. And then you're going to get alkenes due to elimination from the intermediate carbocation, right? So let's take a look at that reaction. I think I have a blank screen and I can show you what it is. Oops. Okay, so let's take a look at this. So I want to explain what's going on here. Okay, so notice, maybe I should point out that this product, the water, after losing, the water replaced the leaving group at the position the leaving group was at, right? But in the second product, the water ended up over here. See that? And so that's a rearrangement. And let's see how that takes place. So the first step is loss of the leaving group. So we lose the leaving group and we form the carbocation. Okay. The leaving group goes. I'll show it that way. Now, in SN1E1 reactions, you need to draw the structure of the carbocation to evaluate whether it'll undergo rearrangement. And in this case, if you draw it, you see there's an H here, and you can do a hydride shift. Okay. You do a hydride shift, what happens? I'll put the hydrogen there. There's another one here. There's a hydrogen I'm not showing. And now you're going to move another hydrogen over there. So that's neutral. This carbon loses a bond, and so it becomes positive, right? Right. So you go from a secondary carbocation here to a more stable tertiary. And so that shift, that rearrangement will take place. Remember, if you can form a more stable carbocation by a hydride or a methyl shift, it will happen. And now, how do we account for the products? Well, we have water as a solvent. The water can attack this positive charge there. Maybe I should change the color of this. The water can attack that positive charge. That will generate this. Okay. And then that loses, that's an acidic hydrogen, that loses H plus. And that gives us that product. I'll call that product 1. That's the same as that's that product. Okay? That accounts for that product as reactivity of the initial form carbocation. And now you have a rearranged carbocation. So water can attack it, right? Water can attack it, and then what's going to happen there? Then water ends up attached there, right? And then that's the acidic proton is lost. And in that case, you form this product too, see? Where the OH is attached there. Okay? So the problem with SN1 reactions is not only that you lose the stereochemistry of the starting material, but they can rearrange too. They're really lousy reactions for synthetic organic chemists. You want it to go SN2 if you can, because you know exactly where the nucleophile will attach itself, and you can predict exactly what the stereochemistry will be, okay? And I'm not going to show you this, but these carbocations here and here can also eliminate an adjacent H plus to form the alkene products. And that would be good practice to try to do that, okay? All right, guys, so